A substation contains a coordinated set of high voltage and medium voltage equipment designed to control, protect, transform, and distribute electrical power safely and reliably. Key components include transformers that change voltage levels, circuit breakers that interrupt fault currents, and disconnect switches that provide visible isolation for maintenance. Busbars distribute power between incoming and outgoing feeders, while instrument transformers, CTs and VTs, supply accurate signals for metering and protection. Surge arresters, lightning masts, and grounding systems protect the substation from overvoltages and lightning strikes. Additional equipment such as relays, control panels, capacitor banks, switchgear, cable terminations, and cooling systems work together to ensure the substation operates efficiently, remains safe for personnel, and maintains continuous supply to the grid. Let's discuss one by one. GIS versus AIS. GIS uses SF6 gas insulation to achieve a compact, high-reliability substation footprint suited for urban or harsh environments. AIS uses air insulation, offering lower cost, easier maintenance, and larger space requirements. The choice depends on land availability, environmental conditions, and long-term operational priorities. Circuit breakers. Circuit breakers interrupt load and fault currents using arc extinguishing mechanisms to protect power systems. They operate automatically during abnormal conditions to isolate faults. Their reliability directly supports grid stability and equipment safety. Disconnect switches, isolators. Disconnect switches provide visible isolation for maintenance and switching under no-load conditions. They lack arc quenching capability and therefore cannot interrupt current. Their role is mechanical separation of equipment for safe access. Difference: disconnectors versus circuit breakers. Circuit breakers interrupt load and fault currents automatically, while disconnectors only isolate de-energized circuits. Breakers provide protection, isolators provide safety isolation. Both work together to ensure safe system operation. Transformers. Transformers change AC voltage levels through electromagnetic induction while maintaining frequency. They are categorized as step-up and step-down based on voltage conversion direction. Transmission and distribution rely on staged voltage reduction from hundreds of kV to consumer levels. Buchholz relay. A Buchholz relay detects internal transformer faults by sensing gas accumulation or sudden oil movement. It provides alarm and trip functions for early protection of oil-filled units. Gas sampling supports diagnostic analysis. Sudden pressure relay. A sudden pressure relay detects rapid pressure rise inside transformer tanks, indicating internal faults. It provides fast tripping independent of electrical relays. This early detection limits damage and improves transformer protection. Pressure relief device, PRD. A PRD vents excess pressure from transformers when internal levels exceed safe limits. It opens automatically and reseats when normal pressure is restored. This prevents tank rupture and ensures operational safety. Rupture disc. A rupture disc bursts at a calibrated pressure level to rapidly relieve transformer overpressure. It is a single-use device that must be replaced after activation. Its instantaneous action prevents catastrophic tank failure. Difference: rupture disc versus PRD. A rupture disc is a disposable pressure burst device, while a PRD is a reusable relief valve. The disc provides one-time rapid venting, whereas the PRD opens and reseats automatically. Both belong to the pressure relief category but operate differently. Difference: rupture disc versus sudden pressure relay. A rupture disc physically vents pressure, while a sudden pressure relay detects pressure rise electrically. The disc protects mechanically against tank rupture. The relay initiates protective tripping. Both address internal faults but via different mechanisms. Thermometers and thermal relays. Thermometers provide passive temperature indication, while thermal relays actively trip equipment under overheating. Thermal relays protect motors and transformers by preventing thermal damage. Both enhance monitoring and safety. WTI and OTI. WTI measures transformer winding temperature, while OTI monitors oil temperature. Both indicators trigger alarms and cooling actions to maintain safe operating conditions. They are essential for thermal management of transformers. Oil level indicators, OLI and MOI. OLI devices show transformer oil level, while MOI uses magnetic coupling for leak-free indication. MOI often includes alarm switches for abnormal levels. Both ensure proper insulation and cooling performance. Breather with silica gel. A silica gel breather dries incoming air to protect transformer oil from moisture contamination. Color change indicates saturation and need for replacement. It preserves oil insulation quality and extends equipment life. Earth switch. An earth switch grounds de-energized circuits for personnel safety. It discharges trapped charges and provides a low-impedance fault path. Interlocking ensures it closes only when isolators are open. Difference: isolator versus earth switch. An isolator provides visible air gap isolation, while an earth switch grounds the isolated section. Interlocks prevent unsafe operations. Together they ensure mechanical and electrical safety. Bushing. A bushing insulates high-voltage conductors passing through grounded transformer tanks. It prevents surface flashover and ensures safe current transfer. Bushings are critical for HV equipment integrity. Voltage transformer, VT. VTs step down high voltages for safe metering, protection, and control. They provide accurate, isolated secondary signals. VTs enhance safety and enable precision monitoring of HV systems. Current transformer, CT. CTs step down current for metering and protection while maintaining proportionality. They isolate secondary circuits and feed relays and meters. CT secondaries must never be left open when primaries are energized. Cable sealing end. A sealing end transitions between overhead lines and underground cables. It provides insulation, mechanical support, and environmental protection. It ensures safe termination of HV circuits. SF6 to air bushing. This bushing connects SF6 insulated GIS to air-insulated systems or overhead lines. It maintains dielectric integrity across two insulation media. It is essential for hybrid AIS GIS substations. Busbar. A busbar distributes power between incoming sources and outgoing feeders. It supports multiple configurations for reliability, flexibility, and maintenance. Its design is central to substation operability. Busbar types: AIS, GIS, enclosed. AIS uses air insulation with larger footprints. GIS uses SF6 for compact, protected installations. Enclosed busbars offer additional mechanical protection depending on system design. Busbar arrangements. Configurations include single, sectionalized, double, main transfer, 1.5 breaker, and ring systems. Each offers different levels of reliability, cost, and flexibility. Selection depends on load criticality and expansion needs. Single busbar. A simple, low-cost arrangement where all circuits connect to one bus. It is easy to expand but suffers full outages during bus faults. Maintenance requires circuit shutdowns. Sectionalized single bus. Divides the bus into sections using bus sectionalizers. Improves reliability by isolating faults to one section. Allows partial operation during maintenance. Main and transfer bus. Includes a main bus and an auxiliary transfer bus for bypassing breakers during maintenance. Enhances operational flexibility with minimal interruption. Protection remains on the main bus. Double bus single breaker. Two buses feed circuits via a single breaker and bus coupler. Provides flexibility for maintenance and switching between buses. Protection is complex and relies on couplers for continuity. Double bus double breaker. Each circuit has 2 breakers connecting to 2 buses. Offers highest reliability and uninterrupted maintenance capability. High cost and space requirements limit its use. 1.5 breaker scheme. 2 buses serve circuits using 3 breakers per 2 circuits. Allows any breaker to be isolated without losing supply. Provides excellent reliability with moderate cost compared to double breaker schemes. Ring/mesh bus. Circuits connect in a closed loop, allowing feeding from 2 directions. Requires directional protection and is difficult to expand. Supports high continuity with limited scalability. Auxiliary transformer. Supplies low voltage power for control, lighting, and station services. Ensures substation functionality independent of main power circuits. Supports reliability by isolating auxiliary loads. Neutral grounding resistor, NGR. Limits ground fault current by adding resistance in the neutral path. Enhances equipment protection and enables selective fault detection. Improves system safety during earth faults. Low versus high impedance ground fault. Low impedance faults produce high currents easily detected by protection devices. High impedance faults produce low currents that may remain undetected. Surface conditions often dictate impedance type. HV fuses. HV fuses interrupt overcurrent in high voltage equipment like transformers and capacitor banks. They provide simple, fast fault clearing. They enhance equipment protection in distribution systems. Surge arrestor. Surge arrestors clamp transient overvoltages and divert them to ground. They offer high resistance in normal conditions and low resistance during surges. They protect equipment from switching and lightning surges. Lightning arrestor rod/mast. A lightning mast intercepts direct lightning strikes and diverts current safely to ground. It protects structures by providing a preferred strike point. It covers an area with a defined protective zone. Difference: surge arrestor versus lightning rod. A lightning rod protects structures from direct strikes. A surge arrestor protects electrical systems from transient overvoltages. One handles physical lightning, the other handles electrical surges. Both are essential but serve different functions. Capacitor bank. Capacitor banks supply reactive power to improve power factor and reduce system losses. They increase system capacity and stabilize voltage. Banks may be fixed, switched, or automatic. PLC, substation communication, fiber optics. Fiber optic communication links PLCs and IEDs with SCADA using protocols like Modbus TCP/IP or IEC 61850. Optical ground wire enhances speed and immunity. It forms the backbone of digital substations. PLCC, power line carrier communication. PLCC sends high-frequency signals over transmission lines for control and teleprotection. Line traps and coupling capacitors isolate and direct carrier paths. It serves legacy communication needs between substations. LMU, line matching unit. LMUs match impedance between transmission lines and PLCC terminals. They filter signals and protect equipment from surges. They ensure efficient and reliable carrier communication. OPGW. OPGW integrates grounding and fiber optic communication in one cable. It provides lightning protection and high-speed data transmission. It replaces older PLCC systems in modern grids. Protection relays. Relays detect abnormal conditions and initiate tripping based on reliability, selectivity, sensitivity, speed, and stability. Their philosophy ensures fault isolation with minimal system disruption. Digital and numerical relays dominate modern systems. Zones of protection. Each equipment zone trips independently when faults occur within its boundaries. Overlapping zones prevent unprotected segments. Proper zoning enhances system dependability. Relay types. Electromechanical, static, digital, and numerical relays offer progressively advanced control and communication capabilities. Numerical relays integrate multiple functions, logic, and data storage. They form the core of modern protection systems. Overcurrent relay types. Instantaneous, definite time, and inverse time relays provide graded overcurrent protection. Inverse curves vary from normal to extremely inverse. Coordination ensures proper fault discrimination. Differential relay. Detects internal faults by comparing incoming and outgoing currents. Any imbalance triggers tripping, protecting transformers and generators. It offers fast, selective internal fault clearing. Percentage differential relay. Uses operating and restraining coils to avoid false tripping during external faults or inrush. Trips only when differential current exceeds a percentage of through current. Enhances stability and sensitivity. Distance relay. Measures line impedance to estimate fault distance and protect transmission lines. Operates within defined zones for fast, selective clearing. Essential for long line protection. Lockout relay, 86. Provides mandatory manual reset after severe faults, preventing automatic re-energization. Coordinates multiple tripping functions for critical equipment. Ensures safety in post-fault inspection. Master trip relay, 94. Initiates breaker tripping and auto resets for temporary faults. Supports wreck losing schemes and continuous operation. Used where rapid automatic clearing is required. Auxiliary relays. AUX relays multiply contacts, provide interlocking logic, and support tripping functions. They enable complex control circuits and SCADA interfacing. They are foundational components of protection schemes.